Hi students, welcome to today's class. In this session, we are studying about error detection and correcting capabilities of a linear block code or minimum distance of a block code. Okay, so let V equal to V0, V1, V2, etc. be a binary tuple. Minimum distance determines the random error detecting and random error correcting capability of a code. Okay, now instead of C code word, we are selecting the variable V for code word. Okay, so here V means the code word, and the minimum distance, which means that is nothing but it is a random error detecting and error correcting capability of a code. So by using minimum distance, we are detecting and correcting the errors. The Hamming weight or simply weight of V denoted by W of V. So some parameters will be discussed here. That is, Hamming weight is the first parameter of V is denoted by W of V is defined as the number of non-zero components of V. So what is Hamming weight? Hamming weight is nothing but the number of non-zero elements in V. So let V and W be two tuple, then V is equal to 1 0 0 1 0 1 1 and W is equal to 0 1 0 0 0 1 1. So the Hamming weight can be written as the Hamming weight of V is W of V, which is equal to the number of non-zero elements. So here the number of non-zero elements is 1, first position, 2, 3, 4. So there are 4 non-zero elements in code word V. So we have W of V equal to 4. So look, W is the code word and this W is the weight. So it has 1, 2, 3. There are 3 non-zero elements in W. So the Hamming weight of W is equal to 3. Okay. So this is all about Hamming weight. Now the second parameter is Hamming distance or simply distance between two chord word V and W denoted by distance D of V comma W. So Hamming distance is nothing but distance between two chord word. So let V be a chord word and W be a chord word. Then distance between V and W can be written as D of V comma W and is defined as the number of places where they differ. So distance between V comma W is nothing but there will be a two chord word. So by comparing these two chord words, the number of places where these are different, which is equal to the distance between that chord word. Okay. Now the Hamming distance matrix function that satisfies the triangle inequality. This Hamming distance, which is satisfying the triangle inequality, that is nothing but V, W and X are 3 tuple. Okay. Then we have V, W, X. Okay, 3 chord word. Then distance between distance between V comma W. So this is the distance between V comma W. So distance between V comma W plus distance between W comma X. This is the distance between W comma X. So this is the distance between V comma W and this is the distance between W comma X, which will be greater than distance between V comma X. Okay, so by adding this distance and this distance, which will be greater than this distance. So this is the triangle inequality. So this is using here. Okay, so from this it is clear that this is distance between V and W is this and distance between X and W is this. So by adding these two, obviously this is greater than distance between V and X. Okay, so this is the triangle inequality equation. From the definition of Hamming distance and definition of modulo 2 Hamming distance between V and W is equal to Hamming weight of some V and W. So there is a relation between distance between, that is Hamming distance and Hamming weight. So this is discussed here. This is mentioned here. That is distance between V and W. This is Hamming distance, which is equal to weight of V plus W. So by adding two chord word and we get a third chord word. So the weight of third chord word, which is equal to the distance between the first two chord word. So this is the equation 2. So we have V is equal to 1 0 0 1 0 1 1. Then W is equal to 0 1 0 0 1 1. So distance between these two is nothing but the how much places they are differ. So we are looking first place. First place both are same. So no difference obtained. Second place, both are, distance is nothing but how much distance, the number of places which they are differ. That is called a distance between two chord vectors. So first place they are equal, second place is equal, third place is equal, but fourth place is not equal. We have 1 and W have 0. So fourth place has different, and fifth place is equal, fifth place, sixth place is different, and seventh place is different. So distance between these two chord word is 1, 2, 3. So by looking the difference in their places. Okay. So we get 1, 2, 3. Three places. In three places, these two vectors are different. Other places, they are same. So distance between V and W will be 3. Okay. Now we are finding V plus W. So by adding these V plus W, we are adding modulo to addition. By adding 1 plus 1 is 0. So no carry because it is modulo to addition. 1 plus 1 0, 0 plus 0, 1, 0, 1, 1. So this is the value for V plus 1, that is 1, 1, 0, 1, 0, 0, 0. So we have V plus W is equal to this. So from this equation it is saying that the distance between V comma W is equal to the sum of vectors weight. So this is V plus W and its weight is nothing but number of non-zero values. Here number of non-zero values is 3. So weight of V plus W is 3. So the distance between V comma W and the weight of V plus W both are 3. So they are same. So we are proven this equation. Okay. So given a block C, the minimum distance of is denoted by d min and is defined as. Now we are producing a new block, that is C. So d minimum is equal to minimum of d distance between these two vectors. So we are defining a new term, that is minimum distance, which is nothing but the minimum distance between V and W. That is d minimum is equal to minimum distance between V comma W, where V and W is an element of C chord word. Okay. If C is a linear block chord and sum of two chord vector and chord vector if also a vector. Okay. If we add V plus W, it's a chord vector. The sum of the chord vector V plus W is also a chord vector. From equation 2, Hamming distance between two chord vector is equal to Hamming weight of a third chord vector in C. Substitute equation 2 in 3, then we get d minimum is equal to. So from the equation 2, we know that distance between V comma W is equal to weight of V plus W. So we are writing this minimum distance of weight of V plus W. So V plus W is the third chord word which is also in C chord word. So let it be X. So d minimum is equal to minimum of W of X. X is also an element of C and X is not equal to 0. So d minimum is equal to weight minimum. Okay. So we got the distance, the value as d minimum is equal to distance between two vectors, and also we have the equation d minimum is equal to minimum weight of a vector, where V minimum, W min is the minimum weight of the linear weight chord. So minimum distance can be found by founding the minimum weight also. The minimum distance of a linear block chord d min is an important parameter of the chord. It determines the error correcting and detecting capability of the chord. So in order to find the error correcting or error detecting, the term d minimum is very important, which means that if a transmitted is received, we want to relate this received vector with the other vectors. So in that case, the importance of d minimum is very important. We are taking the vector with the minimum distance. Okay. So if suppose an n comma k linear block code is required to detect and correct all error pattern over a binary symmetric channel whose Hamming weight is less than or equal to t. That is, if a code vector Ci is in the code is transmitted and the received vector R is equal to Ci plus E. Of course, we require that the decoder output C cap is equal to Ci whenever the error pattern E has a Hamming weight W of E less than or equal to T. Is something here we are saying that if there is an n comma k linear block code, then it has a error which is less than or equal to t. Okay, and whose Hamming weight is also less than or equal to t. if the code vector Ci, that is R, received vector R is equal to Ci plus error. That is Ci, we are writing Ci means we don't know about the code word. So received vector is something Ci plus E. So we decoder output may be C cap equal to Ci. C cap is nothing but estimated code word, which is Ci. Whenever the error pattern E has a Hamming weight We less than or equal to T. So this T is the error. So the weight of the error should be less than or equal to T. Okay. So we assume that the 2 raised k code vector in the code are transmitted with equal probability. Then best strategy for finding the decoder is to pick the code word is closest to the received vector at R, that is the one of which the Hamming distance Ci comma R is the smallest, which means that graphically we can represent this other than, okay, which means that we received a R vector. From this R vector we are finding Ci and another vector Cj. So we are predicting the code word. This may be the code word or the other may be. So we got a list of code word. So these are suppose by receiving the received vector, we are concluding that this Ci, Cj, these two are the transmitted vector. So we want to find whether Ci or Cj is the transmitted vector. So by receiving, we have some assumptions that some set of code word, let that code word be the transmitted code word, then Ci or Cj. Then we are looking the minimum distance between R and Ci and R and Cj. Okay, we are looking the distance between R and Ci and R and Cj. So by calculating the distance, we will get a conclusion that if the distance between R and Ci is 2 and the distance between R and Cj is 3, then we are selecting the minimum distance. So if we have a list of code word to select, then we will calculate the distance between the received code word and the list, and by calculating the distance we are selecting the code word with the minimum distance between R and C. Okay, so this is how it is useful for error detection and correction. That is saying in this part. Okay, with such a strategy, the decoder will be able to detect and correct all error pattern of Hamming weight W of E less than T, provided that the minimum distance of the code is equal or greater than 2T plus 1. So, in order to get the error from this way by using minimum distance, there should be some assumption that the two code vector should have the distance 2T plus 1 equal to or greater than the distance 2T plus 1. So, this can be explained by using a geometric interpretation. Okay, so this is Ci and this is Cj, two code word. So there is two condition of occupying Ci and Cj. That is, this is disjoint code vectors. So Ci is here. The Ci has a radius t, that is error. Ci get error in this session and Cj get error in this session. Okay, so if you are receiving a R, we want to calculate, we got an R here. So the distance between Ci and Cj should become equal to or greater than 2T plus 1. This is the center to this boundary is T. The Ci, this is Cj. The Cj center to this boundary is T. So this is T plus T is 2T. So this distance, that is distance between Ci and Cj, should be, from this figure it is clear that it will be 2T plus 1 because this value is T and this value is T. So this is greater than 1. So we have 2T plus 1. So it is, so this is the condition to get an correct code word from the received vector. So this is another condition, that is Hamming distance Ci comma Cj is less than 2T. That is, this is Ci and this is Cj. This is T value. So if we receive R here, there is a the distance between CI and R and CJ and R may be equal. So the receiver will get a confusion that whether we want to take CI or CJ. So we already said we should look the distance between R and CI and R and CJ. We select the minimum distance between R and the code word. So if R received here, the distance between R and CJ and R and CI is equal. So the receiver or the decoder does not get a minimum distance from this section. So it should be like that. CI and CJ should be disjoint vectors and they should maintain a minimum of 2t plus 1 distance. Okay, so the two spheres are disjoint in figure A. For this condition, satisfied distance CI comma CJ is greater than equal to 2t. If then the code vector CI is transmitted and the Hamming distance dCi comma r is less than equal to t. Okay, so if Ci is transmitted, the distance between r and Ci is less than t, it is clear that the decoder will pick Ci as it is the closest code vector to the receipt vector r and Cj is very far from r. So if r is received, we only select Ci. Okay, so in figure B, the spheres Ci and Cj are intersect and the Hamming distance is less than 2t. Here, if Ci is transmitted, there exists a receipt vector r is close to Cj as it is to Ci. So, r is close to Ci and Cj. Clearly, there is a probability of decoder picking the vector Cj which is strong. So, Ci is transmitted. So, r is the receive vector. So, our distance between Ci and r distance between Cj and r are same. So, the decoder, there is a possibility of a decoder to select Cj also. So, this is a wrong selection. So, in order to get a correct selection of code word, the all code word in a set should have a maximum distance of 2t plus 1. Okay. So, we conclude that n comma k linear block code has the power to correct all the error pattern of weight t or less if and only if we can correct the error if and only if distance between Ci and Cj should greater than equal to 2t plus 1 for all Ci and Cj. The smaller distance between any pair or code word is a code is the minimum distance of the code daemon. Therefore, we may state that n comma k linear block code of minimum distance daemon can correct up to t errors if and only if the minimum distance is greater than equal to 2t plus 1. That is d minimum this plus 1 will be given here and 2 will be placed here. So d minimum minus 1 by 2 is greater than equal to t. So that is t is less than or equal to 1 by 2 d minimum minus 1. Okay, so this is how we are selecting the t. So by getting the d minimum value, we can find out the value of t, that is the error value. From this we can find the error. Okay, so for finding and detecting an error, this rule should be satisfied. That is, the distance between two code words should be 2t plus 1. Otherwise, we cannot detect any errors and correct the errors. So, this rule should be satisfied. Okay, so this is how we are finding or this is how we are finding the error and correcting the error in linear block code. So, that's all about today's class. Thank you.